All right, we're on the last chapter. We're going to discuss, in this chapter, we're going to talk about two pretty important aspects. Correlation, and the next one, section 2, deals with regression. The difference between the two is correlation. What it does, it compares two different outcomes on the same graph to see how each of the data points are related to each other. The first thing we do is we create a scatter plot. What is a scatter plot? What does it look like? Bunch of dots. Yeah, it's a bunch of dots. It's a graph. It's a graph representing the paired data set. What that means, in algebra, we call this an ordered pair. You have a horizontal and a vertical component. Because each data that you have is a result of an independent variable and dependent variable. There's what you're observing and what the outcome is. So this is what we're doing. Now when we take all these individual data and plot them on the same graph, interesting things can happen. Take a look at this. Take a look like this. Take a look at that. Or they can even have a curve to them, a unique shape. Whatever happens with the graphs, you have no control over it. All you're doing is just plotting them and representing what they have. Now, why is this important? Why is looking at how the dots are arranged, why is that important? What can we do with them? How? And what's that going to be to the data? What is a correlation then? You're using a word now, you have to define the word. There's what?
Because correlation, they don't cause each other, right?
Right. Correlation does not imply causation. Nope. It's like saying if you had high SAT score, that means you're going to have a high GPA. That's not true. It has no correlation whatsoever on your SAT score versus your GPA. So you use the word correlation. Let's define what that means. Correlation happens between data sets. This exists between two variables when one variable is related to the other. Variable in some way. Okay, here in this definition, we use the word variable. We have two variables. What are our two variables? Our two variables are x and y. What a correlation does is if there is a correlation between the x and y variables, then they're going to have a more uniform look to them. Even this one. What this one tells us is this: there's no correlation between the data, meaning there's no relationship between the x variable and the y variable. You can look at correlation approximately as the slope, not the number of the slope, but how definitive it is. Whereas in the next section, in regression, then we're going to define linear equations. We're going to define the actual value for the slope and the actual value for the y-intercept. We're going to have linear equations. Now, with this one, since the data seems to be forming along a certain line, this line is called the line of best fit. Again, that line is going to be defined next week when we do regression. But as you can see, the closer the data is along that best fit line, that means we have a high correlation. We say here we have a very high positive correlation. Because it's a positive. Now, we can even add one more word in there. It's a very high positive linear correlation. We're going to be focused, since we're just an introductory course, we're going to focus on linear correlations. There are other types of correlations that can exist. So just because we have this in a graph, it doesn't mean that we have a very low or no correlation between the variables. Conversely, if we have one that's going down from left to right, we say this is a very high negative linear correlation. And the last one, we can say we have no linear correlation. Does that mean the x and y values are not related in some way? No. It just means that they don't form a linear correlation. They could be quadratic, they could be cubic, they could have some other types of correlation that goes to it. So when we talk about correlation, what we use here is called the Pearson R value. The Pearson R value tells us what is the level of correlation, whether it's positive, negative, whether it's high, whether it's medium, whether it's low. What is the level of correlation between our X and Y values? The values of R have to range between -1 and 1. I think I put in the packet I gave you. Yeah, if you look at on page 4 of the packet, if your R value, the closer it is to positive and negative 1.0, we can say that that's an extremely high positive or negative correlation. Or we can say, as they're saying, it's a perfect correlation. What that means, if it's a very extremely high, I mean you're very, 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 very close. If you get to exactly 1.00, what that means is you can predict what's going to happen. Because the X and Y variables are such a very high relationship between them that you can predict what's going to happen in any given X value. So if we look at this, the further, because at 0, it's no linear correlation between the data. I mean, you can't use 1 to predict anything. There's absolutely no linear correlation. And at the extremes, at -1 and +1, it's extremely high positive or negative correlation. Now, from there, as we go from the extremes to the no, it's a matter of gradation. This is where the person themselves, where there's no written rule exactly what it should be. But these are ballparkish ones. So now, since 0.8, it's pretty close to 1.0. It's not extremely high. We can say it's very high correlation. Or we can say that it's a strong correlation. And we can do a middle one, say at 0.4, 0.5, negative 0.5, and positive 0.5. And these, since they're in the middle of the road, moderate negative or a moderate positive correlation. Now, if you use the strong, then for the inside ones, we use very weak. Linear correlation. So again, it's how you define it yourself, describe it yourself. Whenever you make a statement with respect to what your R values are, you have to put the reason behind it. So what exactly is, where does the R value come from? All right. We have two standard types of equations that we use for the R values, depending on how we're going to use them. Traditionally, the R value we use for the Pearson is n times the summation of xy minus the summation of x times the summation of y all over. We have two separate radicals on the bottom, one dealing with x, one deal with y, because remember, they're independent variables. So we have n times summation of x squared minus the summation of x squared, n summation of y squared minus the summation of y squared. I'll get that one for you also. This is used for calculations. The other format we use is the summation of your z-score with respect to your x times the z-score of the y over your n minus 1. This one is used for understanding. If you just want to understand what's going on with your data set, that's the one you'll use. Here's a note really quick. Does everybody know what the summation symbol stands for? What does that mean? Right. So what this means is it's supposed to look like this. It's supposed to be an index term where, let's say, x represents the set of your data. So there's my set x. What the subscript means, the thing on the bottom, is this first one is x sub 1. The second one is x sub 2. The third one is x sub 3, and so on and so forth, because it labels which position that value holds. So since I have 7 of them, that's what my n represents. I would have summation of I equals 1 to 7 of x sub I. What this means is I start off with I equals 1. And because this means summation, I add the next one. I keep on doing this until I get to 7. And now what is x sub 1? X sub 1 represents 1. X sub 2 is 3, 4, 5, 6, 7, and 4. That's how it works. That's how you would refer to your data set. And then this means we add them all up. So we have 3 plus 7 is 10, plus 10, plus 10. So our data set equals 30. That's how it works. We need to know this because look at our formula. We have a whole bunch of these. In the bottom, many students get these confused. Note number 2. The summation of x squared is not the same thing as the summation of x squared. That's what I get to. They do not equal. Why? Yes, that's what it said. But no, now, what will be the difference in the answers? Okay, let's look at. We had our x values. We use the same ones we just had. We had 1, 3, 4, 5, 1, 3, 4, 5, 6, 7, 4. Summation of x is you add up all those. And then if I take the summation of x and I then square it, it equals 900. As opposed to summation of x squared. What this one says is I have to square my x's first. These are my x's. I square them. So it's 1. 3 squared is 9. 4 squared is 16. 25. 36. 49. 16. Now, all I got to do is just add up those. So it's 10, 26, 51, 45, 96.
How much? 36 and 49 and 45.
Oh, 85. That's 136. 136 and 16 is 152. Clearly, a big difference between the numbers. Order of operations. This one says I add up all the numbers first and then square it. This one says I square the numbers first and then add them. All right. Because if I'm not mistaken, the packet I gave you on the back of page 10. let's find the R value of this data. So remember the formula for R was n times summation of xy minus summation of x, summation of y, radical n summation of x squared minus summation of x squared, n summation of y squared minus the summation of y squared. So in order to do this, what do we need to find? Do we have n? What is n? What does n represent? The number of pairs that we have. 1, 2, 3, 4, 5, 6, 7. So n is 7. So anywhere we see an n, we put a 7. Now we gotta start building each one of these numbers. The first thing we gotta find, well, can we find these two? The summation of x, the summation of y. Go ahead and find those. Get your sub calculators out. This is a math course. Let's see what we do next. Everybody should be working. If I see anybody sitting there doing nothing, I'm just gonna stop and let you finish. If I see anybody just sitting there, I'm just gonna have them come to the board and do it for us. There's a blank board right there that needs somebody to work on it. So if I see anybody just sitting there doing nothing, they get to volunteer. So we add up the x's, the y's, We plug those in on the top in the numerator. Then we have to find the summation of x times y, which means you'll take x times y, multiply these together, and add them all up. And that there's your summation of x and y. There's your summation of x. There's your summation of y. On the bottom, we know what n is. And inside the parenthesis here, we know summation of x. That's the same as that number. It's just squared. Summation of y, that's the same as that number, just squared. So the last thing we have to do are these two columns. The summation of x squared and the summation of y squared. So this is x squared, and this is y squared. So how do you get x squared? Yeah, you just take the x and square it. Same thing with the y's. Take the y values and square them. So this one is 98 squared. This one's 88 squared. I do that to each of the terms. Then from there, I do what? I add them all up and down.
Wait, which number did you say?
What's that?
Which number did you split? The X one or the
X. It says x squared. Where's x? Right here. Squared means squared. 98 squared is that. This is the y value squared. So yeah, this tells you what column you have to go to get the number and square it. $59.13. 52733. Then what do? The algebra. On the top we have n equals n equals 7. So my formula is on top 7 times the summation of xy minus the summation of x times the summation of y. That's the numerator. That's your number on top. Now I got to do both of these inside the radicals. I take the 7 times the summation of x minus the summation of x squared. So I'll do each one of those separate ones. So on the first bottom one, we have 7 times the summation of x squared, which is this one, minus the summation of x squared. I have to take the square root of that. So that is my first number. 68.86. So this first part is 68.862. I gotta do the same thing with this one. So that one's gonna be n times the summation of y squared minus the summation of y squared. Can't be. Oop, I forgot to do that. Doesn't do something. This one I need J2 times there. So it should be x squared, which is f10. Take the square root of that. Five 5.7315. Now I take multiply these two and do the division. So I have that number divided by this number times this number. Eight, 5, 4. So there's my R value. Most of y'all have just been watching me, so have fun doing the homework. It does take time. You have to know how to do this. So that's why in class it's a good practice. So now what do we do with that number? What does that number represent? What's that? But what does it do for us overall? Yes. So how would we define? Yes, this is the first part. It is the correlation. But what do we know about the data then? Is it high or low? What is it? How would you define this one? With what we just talked about a second ago. Yeah, it's a very high positive correlation because it's pretty close to 0.8. Okay, so that's the first one. It tells us what our data does, the relationship between our data. But now, how do we relate this to hypothesis testing? How does this relate to our hypothesis testing? On the back of your packet, I gave you this table. Another table that may be easier to see. Well, let's use this one. Now, how would we use this table?
saying that even though there's a positive correlation, it's not strong enough?
How do we know? Well, no, we're what we're doing now is we know we have a very strong positive correlation. But now, how does it relate to hypothesis?
Well, if you needed 0.05 for that critical value, you would need a little bit higher, because actually 0.72, right? And that's 0.75.
Yeah, so the way you use this table, what's our n? 7. And typically what we do is we use a 0.05. You would use a 0.01 if you want to make sure it's 99% positive. So here's our critical value. 0.754. So what that means is in our test, let's say we had 0.7, was it 7? It was 0.754. That's the critical value. Where does ours fit with respect to this? Because if you look at your packet, I think I gave you the chart of determination. Let's see here. Oh, here it is. It's not in your packet. I'll give it to y'all. Critical values and computed R values. Your critical value is what comes from the chart. Your calculated R value is this one, the sample data. If it's within the critical region, then you have a correlation. If it's outside of that, then you don't have a correlation. Now, how does that relate to your hypothesis testing? Same way. If it's within the critical region, you reject the null hypothesis. So since we're here and our value came up to be, what was that one? 7283, which is over here. With respect to hypothesis testing, we can't reject the null hypothesis. So that's how it relates to hypothesis testing. Because remember, everything we do has to go to the basis of a hypothesis or non-hypothesis. Go ahead and write this one down. I'm sorry. I thought I had that in that other packet. And I will write down the decision criteria in words. Because this is exactly the same thing we've been doing in the last chapter, is we use the table to find our critical values. That defines our critical region, our alpha region. And then we do the actual test, either the p-value test, the confidence interval test. And then from there, that tells us where it sits. Just this. Now, if we had the same values, the conditions for a t-test, we can use a t-test here as well. This is simply using this table to the value. Here's what we call the decision criteria. Your decision criteria. If the absolute value of the computed value, that's the R that you actually worked out yourself, of R exceeds the value from table 6, that chart we just showed you, then we conclude that there is a significant linear correlation. Otherwise, there isn't sufficient evidence to prove that. To support the conclusion of, oops, I don't have enough room, of the significant linear correlation. So that's if you use the table for that. There is a t-test we can use, similar to what that we would use in the p-value. So this is the decision criteria for table 6. For table 6, if you're using table 6. And notice that it has in table 6, whether it's 0.05 or 0.01. Again, this is the non-exactness of the science. There is no way, know which one that tells you what you have to use. You can use whatever you want. If yours succeeds in this one and you want to try this, that means it's even more significant because you're at 0.99. Using the t-test or no, I'll use t-test. It's the student t-test. the degree of freedom here is n minus 2. This is for your t statistic. Then your level of significance alpha, it's usually going to be alpha 0.05. That's usually a standard one that we always use. Calculate and compare the t statistic with the critical values. And here's your conclusion. If the t statistic value is greater than the critical value at 0.05, the null hypothesis HO can be rejected. That means there is enough evidence to support the alternate hypothesis, the H1, that there is some relationship between the two variables. Now, remember, since our degrees of freedom, the n minus 2 has changed, our formula has changed somewhat. So we find the critical value like we normally do. Now we do our t-test. The t-test, the t-statistic test, I should say, the t-statistic test looks like this. T is equal to R n minus 2 over 1 minus R squared. Yes. So once you figure out, for example, you know your n, that's, let's say it's 7. We calculate R, let's use the one they use, 724. The t value would be what? So it's r, which is 0.724 times the square root of 7 minus 2 over 1 minus 0.742 squared. And I do apologize that I didn't play with StatDisk before I brought the stuff here. Because think of it, StatDisk, you enter your data, hit enter, and it's done. So now if we plugged in all this stuff, we get 2.347. So that's your t value. And we use it to compare what we need to. Can the R value ever be negative? What's the range of R? So it is possible. Because what determines that is the numerator. What's on your numerator? Can that ever be negative? Yeah. If this is bigger than this, it's going to be negative. And that's a possibility. And also because of that. Which is why the decision criteria, we take the absolute value. We don't care about the sign. We just say where it's, which end is it going to be, doesn't matter. We compare it to 1. All right, that's the end of that section. We only have one more. The next one we have to do, regression, is now we put everything here. Because all this does in this section is determine, is there a correlation between the X and Y values? We can't do anything else other than that. The next one, when we do regression, we're now going to come up with a formula that looks a lot like this. What is that formula of? What's that? Yeah, this is a linear equation. M is the slope, and B is your y-intercept. This is from algebra. Now, why is this important? Because think about it. All these correlations we talked about were what kind of correlations? Linear correlations. So if it's a very strong linear correlation, that means there's a formula we come up with. Why is this good? Because if we can come up with a formula, then we can predict future occurrences. All right. So that does it for that. Have a great, safe weekend.